Hi everyone, welcome back to our Chapter 14, Calculus 3 class notes. We are now moving into section 14.4 on the chain rule. Now recall from Calculus 1, the chain rule for finding dw dt if w is f of x and x equals g of t. Most of you are probably familiar with just you take x, which is g of t, and you plug it in here, and now you have f of g of t, and you can use the chain rule for a composite function. But I want you to try to remember it this way as well. So dw dt is dw dx times dx dt. So thinking of how you can cancel these differentials dx, it's the same thing. But you can think of this in terms of a branch diagram as follows. So we have to get from the function w, which has the independent variable x, and then x itself has the independent variable t. So to get from w to t, we have to pass through x. So the w dt is going to be the derivative of w with respect to x times the derivative of x with respect to t. And that's kind of how you use these branch diagrams. Now remember, I just talked about above, but for the composite function w equals f of g of t, we can also think of t as the independent variable and x equals g of t as the intermediate variable because t determines the value of x, which in turn gives the value of w from the function f. This thought process led us to our other way of thinking about the chain rule, which was, like I was trying to say above, if you plug in g of t for x, you get w equals f of g of t, and now this is completely a function of t. So the way you use the chain rule now is you take the derivative of the outside function, which is f, leaving the inside function alone or leaving it in there as the argument. So it's f prime evaluated at g of t, and then you take the derivative of the inside function and multiply it, so times g prime of t. For functions of several variables, the chain rule has more than one form, which depends on how many independent and intermediate variables are involved. However, once the variables are taken into account, the chain rule works in the same way just discussed. So we could actually, most of the time, do this if we wanted to get composite functions, but it's really much easier in the long run, especially if you get functions of multiple variables and they have multiple variables themselves, that if you learn the chain rule in this format and use a branch diagram, you'll never get it wrong. So now let's say w is a function of xy, which is differentiable, so a function of two variables. And if x equals x of t and y equals y of t are differentiable functions of t, then the composite function w, which is equal to f of x of t and y of t, is a differentiable function of t. So dw dt is the partial of w with respect to x times dx dt, plus the partial of w with respect to y times dy dt. Or again, if you want the composite function way of doing it, you could do it this way. dw dt equals partial with respect to x, leaving x and t and y and t alone, multiplied times x prime of t, plus the partial with respect to y, leaving x of t and y of t alone, multiplied times y prime of t. Again, the easiest way to remember this is often through a branch diagram. So we think about w having to make its way to t. Well, to make its way to t, it has to go through the variable x and then to the variable t. And it has to go through the variable y and then to the variable t. So the derivative of w with respect to t, which is a complete derivative, that's why it's dw dt, is equal to the partial of w with respect to x times the derivative of x with respect to t, plus the partial of w with respect to y times the derivative of y with respect to t. So that's exactly what we have for the formula, but sometimes it's easier to remember that with the branch diagram. Certainly when we get to more than two variables independent here, and they may be functions of more than one variable on this side, the branch diagram will be very helpful. In any event, here's example 48. Let's use the chain rule to find the derivative of w equals x times y with respect to t along the path x equals cosine of t, y equals sine of t. So actually, that's a circle. We're parameterizing a circle. So w equals x times y along this circle. So in other words, x equals cosine t, y equals sine of t. So if I want the derivative of w with respect to t, and I set up my branch diagram, I see it's partial w with respect to x times dx dt, plus partial w with respect to y times dy dt. Again, there's the formula. So partial w with respect to x, that's y, times dx dt, which is minus sine t, plus partial w with respect to y, which is x, times dy dt, which is cosine t. And then at that point, since I know what y and x are, I'll go ahead and plug them in. Y is sine t and cosine is xt, x of t. I'm sorry, x is cosine of t, so I plug those in. And then I get minus sine squared of t plus cosine squared of t, which is actually cosine of 2t if we use the double angle identity. Right? Cosine of t plus t is cosine t minus sine t sine t. So that's where this comes from.